So what we need basically is exactly this one in a cup of coffee, right? So in order to really wake up, and that's my job now, to really wake you up, guys, somehow, to make it exciting. And that I hope I can do that actually by my talk concerning really these kind of domain wall stuff. And I will really go into domain walls, really only in ferroelectric domain walls mostly. You can also have another talk actually on ferromagnetic and stuff, but this talk will only deal with these ferroelectric domain walls. And in fact, this cup of coffee is exactly the right thing to start with, every morning, by the way. So it's a fully ceramic. We have a really wide band gap, right? So there's nothing really too special to say about this coffee, though that it's dielectric, meaning it has a certain dielectric constant, epsilon. But yeah, if you would apply even your 220 volts from the home, actually on the top and the bottom, there will be no current flowing, right, across the whole cup. Whether it's empty or full doesn't really matter. And what we want to do is now really to engineer domain walls into this coffee pot, like we see here, so to say, to separate two polarizations, left and right. In the simplest case, they're really opposite in direction, up and down, and we have tons of such materials where we do have exactly this kind of type of wall, which is called 180-degree domain wall. You see, because the dielectric constant, parameter, when you order parameter, the polarization is just turning by exactly pi. So, what kind of properties could we expect from such a domain wall? Well, historically, people have been really doing some modeling and really saying, okay, this is exactly something where we have two polarizations up and down, left and right to a domain wall, not knowing too much about the thickness of such a domain wall. And hence, if you do so, mostly in any kind of modeling, whether you do DFT or any other approach, you always go for a so-called full icing model system. That means you expect the polarization and left and right to be fully oriented along one of the axes, meaning plus C or minus C. And that means for the description that you go for so-called tangents, hyperbolic. So that means also if you go and now look on the spontaneous polarization across a domain wall in barium titanate at room temperature, that you have a certain width, that's exactly the position here, where the unit cells, so to say, change, and depending on how strong the electronic correlation is between these electrons within or across the wall, you get a certain width that you can define depending on, these correlation parameters. So this is theoretical work by Hassan. And if you go and now calculate also the optical properties of such a wall, imagine you would take a laser pointer like me, and you can go in actually onto this wall. You just shoot on this laser, on this kind of domain wall. The question is how much of that light would go through, how much would be reflected. And in fact, you can take exactly the dielectric data from before and calculate also how much of a refractive index you have, a refractive index change. So, you would say, well, this is so small, this is like a delta function, it doesn't really care because all the light will go through. Might be you're right, at least what the intensity means. But what does the phase do? The phase can change, so it's like a kind of a material, and if you go across such a domain wall, you get appreciable phase changes. So you have two walls maybe, you can measure it, if 3, 4, 5, and so on. So this is exactly the historic view of a ferroelectric domain wall to be a complete Ising wall, to have nothing special properties than this kind of dielectric properties. Well, we know today, and this is work now from Salia Charifi here in Strasbourg in France, actually that even in ferroelectrics we can have completely different walls, Ising walls, Néel walls, Bloch walls, and she was doing some fantastic work together with a group of Patricia Paruch in Geneva, really using so-called second harmonic polarimetry. So you take the second order of a femtosecond beam, that means, so to say, you look on the second harmonic generation, and you do that really in spatial directions by rotating, so to say, the in-plane polarization. You can also do that out of plane, but it's a little bit more complicated. What counts is exactly this kind of factor here, which is again the piezoelectric constants, as you remember from my first lecture, so to say. These are exactly the ones that we need to know. And they might be completely different at the wall position. And that's exactly the new music to play here. Because with this, we can really explain why we have kind of fields, electric fields, which are Néel-like or Bloch-like. Well, That kind of physics is much more known in the magnetism regime. If you go for divergence, not of the polarization, the dielectric or the parameter in ferroelectrics, but if you go really for the magnetization, and you see that picture again, which is exactly this famous schema and stuff, and there are some kind of really measurements where you find in the phase diagram that. I want to leave this topic. I don't want to talk about the magnetic domain walls, but solely about the dielectric ones actually today. So that's actually the system of interest in our case, which is lithium niobate. And you will see lithium niobate, it's called the so-called Drosophila of optics. It's the same thing like if you take silicon for semiconductor people, because it's so versatile, it has so many good issues. And equally, lithium niobate has the same good properties actually for the optics people. And as you will see in a second, these walls that you can really nicely see here, really sketched. No, it's not sketched. This is a measurement, by the way. So we do a measurement, and you can see we can do that measurement into the depths of 300 microns without cutting open the whole system. So we don't need a TEM or a focused ion beam in order to look inside. But I will bring you to the point, how can we really see on the subtle details, for instance, kind of this location, and you can nicely see that there's a narrowing from top to bottom, so they're really elegantly tailored. And this is exactly the right music that we want to really look at, because this tailoring gives us finally exactly what we want to really measure, this kind of conductivity along the domain wall. So this is the plan for this morning. I will start by introducing you into this kind of domain wall conductivity, what that is and how this all happened. And we will see also during the course that we will have domain walls that we can really clear or declare as P-type or N-type. So we take, again, the same similarity that we have from semiconductors. You guys know, by doping with boron or with phosphorus, we can basically make a system rather electron or hole conductive. And why not to do the same thing with domain walls? That would be very intriguing. We naturally need also kind of modelings in order to explain what we do. And we have two things that I would like to share with you. The one is a random resistant network, something that 2D people are really liking, and also vanadium oxide people, or 2D vanadium oxide people have really doing, or a hopping model, which is a quantum mechanical tunneling model. Most of the part, or one of the very important part, is actually this one here, Cherenkov second harmonic. I will introduce you into a technique that we have developed actually, or adapted, that we can really make some kind of 3D tomography. That means simply you take your system, your cup of coffee, and you go to the microscope and you can basically look inside what is really within the ceramic there. This is also something that actually will give us some kind of dynamic properties. And you see, I've put this really to the bitter end, cool Cherenkov second movies, which I want to really share with you in the end. Hopefully by then everybody's here and awake. Okay, now the main part is clearly also that we want to see now, by using this kind of conductivity, can we get some Hall transport measurements? So as you guys know, Hall transport means we need to apply magnetic fields, and that's exactly what we do now. We apply a magnetic field perpendicular or parallel to the domain wall in order to see whether there's a Hall coefficient to be measured and to see how big that is. So we will also have a look into, if there is time, and Mr. Chairman, you're going to stop me, please, after 1 hour, on the AC or transport properties, and also on the dielectric constants, and a couple of applications that not really on paper, but things that we really do. So, for instance, we can really do a two-terminal memory. That means you have only 2 leads, one in, one out, and finished. And you can do a very, very, very good memory out of these domain walls on a 2-level system. Good. So let's start simple, domain wall conductivity, and the whole thing really started. And that's actually the point where I have to mention Jan Seidel. Jan was actually a former student of mine doing his PhD in Dresden, and then he went to Ramesh in Berkeley. And from there, as you guys know, he's now in Sydney, very well installed at UNSW. And he was the first one at the time actually using the BFO thin films from Ramesh in order to really make 2D, to make a conductive AFM. This is exactly taken from his paper. This is topography, as you see, not too special to see what we see. There's some kind of striations there. This is, so to say, the PFM picture, as you see, out of plane and in plane, so to say, polarization. So the vector goes out or in. And finally, we see here, so to say, also a couple of measurements. This is actually, again, the in-plane polarization, and then we have conductivity map of this one. So he uses two combinations, the PFM that I have introduced and CAFM, conductive AFM. I haven't spoken, but I think Karim has spoken about this, where you take the tip as the top contact, you apply a voltage to the bottom, and hence you have a current that is passing across your system. The tricky thing about that system is you don't know where the current is really passing. Is it flowing along the surface and then to the ground electrode? Is it flowing directly through it? Is it flowing, yeah, you name it. There's so many different pathways, and you have to figure exactly where the right path is. Soon later, actually in the group of Beatrice and Hedda, they were really redoing this experiment and finding that are beyond the 109 and the 180, which is the fully P domain walls, they find also 71s. So if you take the unit cell of BFO, as we know as room temperature, there is also these three types, and they've proven exactly thin film domain wall conductivity in this system again. Soon later, also Patricia's group in Geneva were really demonstrating that PCT is a system and so on. And you see, these are all thin film materials. I'm a little bit skeptical always with thin films because on the one side, it's not so easy to really look on stoichiometry. So a small deficiency of oxygen, as I was really demonstrating already in the first talk, really gives you some kind of conductivity, and hence you signal also, not at the domain wall, but in the domain, can also sparsely conduct. So that means simply that we have to be careful and really find a good way to really prove. I think all these things are safe, but we have been saying, okay, why now to take now our Drosophila, the lithium niobate? So we go away now, we'll leave the thin films and we go to something really that is really grown big, sturdy. And you see actually, these are materials which are really single crystalline materials, really blocks. And you will see that the results I present today are always done on a thickness of a material which is not a thin film, not 50 nanometers, but 200 or 500 micrometers. So it's really thick. So imagine there's a huge difference between conductivity of 50 nanometers and 500 microns. So it's a factor of 10,000 in between. Huh? So from that point of view, we are clear that this material, this lithium iodide, grown like this, and I will break the ice for this here, because simply this is something also that industry likes. This lithium niobate is a full wide bandgap material, has 4 electron volts gap difference. You can dope it if you want. We don't want to do it here. But what you can do, and that's even more intriguing, is it's fully CMOS compatible. So industry likes it simply because you can do everything integrated on a chip level. So what we have been really doing and looking at is these domain walls. Now let's look on domain walls, and we expect generally in a thermodynamic equilibrium that these domain walls are all straight. So you guys know how this goes. You have a nucleation, you have a penetration through, then you have a sideways growth. That's exactly the standard model. Now what if we would stop this kind of process at any point in between? We could stop it early. If you stop it early during the growth process, we stop exactly here. The domain will only grow from the surface into the bulk and then stop at some point. We get spikes. That's exactly what the name is, spiky domains. But have a look on this. What you see already is that, the domain walls are not straight anymore. So they're not parallel to the polarization intrinsically in the system. So they are somehow inclined. Okay, let's have a look on that. You could say, okay, we're going to stop it. It's going to grow through, and then we stop it there before the sideways growth comes, and before the full equilibrium is really set in. So from that point of view, we would have possibilities not to go for really these full straight walls, but also something more fancier. Now imagine also that we would do this, like in the middle case, and this is a magnification of that one. This simply means that the domain wall now is inclined with respect to the polarization vector, right? So we have a certain angle alpha, we call it alpha here, which means if you take now your PFM measurement unit, and you do that on this surface and on the bottom surface, something you cannot do with thin films because they clamp to the substrate. So you just take the single crystal, you flip it over, you measure on both sides, and then hence you get two images where naturally the size of this one is exactly a macroscopic view, let's say, a macroscopic hint that yes, you must have inclined domain walls. So this is the nice thing. You can do this on any such kind of single crystals. You can send it down if you want to, but nevertheless, the handling of that system is easy. We've been doing this exactly on the single crystal. You see here it's 300 to 500 microns. We have different sizes there. And then actually really going and measuring topography, measuring CAFM measurements, PFM, and you see these two pictures look pretty the same. That means a domain wall is a conductive part giving currents of 1.4 picoamps. There's one issue. If we do this in, let's say, in the dark, that means simply we just take all lights off that we have, then the current is really very small. That's exactly the current that we see the dashed line here. The dotted line here. Now we found a trick because, well, as you guys know, if you have a system that has any kind of band gap, you could use any kind of light in order to increase that conductivity. Now, funny enough, that domain wall here wants to conduct much better if you just hit it at the right wavelengths, which is exactly 300 nanometers. So you can induce a photocurrent at the domain wall, and in order to cross-check for that current, you can go separate, you go off the domain wall, and hence do the same experiment, and you will see there's no current there. So that means the band gap, if you are below band gap of the bulk material, the band gap is so high in the bulk that you can differentiate between photo-induced currents flowing at the domain wall and those ones which should be really in the bulk of the system. Well, you see, even if by cranking up this UV volt, we don't get too much currents, it's picoamps, it's still small. Okay, that was the beginning really, and that was in 2014, 2012. Well, the good news is today we are up to 1 milliamp per domain wall, so it's really large currents. How could we do that? How could we improve that conductivity? So what is needed in order to really go for higher conductivity? Well, why not to dope the system like I said before, the semiconductors? Do you put something in? Okay, you have to do it beforehand, before you grow the system and before you cut it open. So we could do some doping, and in fact, there's some kind of activities in this direction, but we could possibly work on the bending. As you remember, this angle alpha is something that could possibly help us in engineering this kind of conductivities. We can do some more photo excitation, so really knowing something about the trap density in the wall and hence activate those ones in the conduction band. We could possibly do some strain. There's some other experiments, you name it. There's a huge possibility of how to increase that thing. So let's have a look. We started really simple by saying, okay, let's take this kind of congruent lithium niobate here, and that per se is always a little bit of magnesium doped. Now this magnesium is the question, is this a dopant in the sense of as you put in boron or phosphorus into silicon, and hence the conductivity properties are changing, or has that some other meaning? Well, the people that grow these crystals have to put this in order to activate the growth of that system. We're doing this actually now on a different set of such crystals, varying this magnesium content from 0 to 5%. And you can also see a couple of really measurements for very low magnesium content. And the big question we wanted to address is the magnesium the one, like a dopant, that increases conductivity? So what we did is simply we were really changing the content and spuriously also annealing the system. And you see nicely, actually, you take a system that has been aspoled, and then you anneal it, and then it's dropping down. So that means simply we have no really clue answer whether the dopant, magnesium in that sense, is really increasing our conductivity. In fact, you will see later, just over the next slide, that this doping has nothing to do with the conductivity, but simply with the pinning of a domain wall. So any defect, whether this is magnesium or whatever, can pin a wall, can pin defects, naturally clear. And if it is an extended defect like a domain wall is, then so to say, that magnesium content, that defect is really pinning the wall that it will stay really inclined. So what we then did at the same time is saying, okay, we want to know now this kind of alpha. So we have already seen one clue possibility how to measure that. We can measure on the top and on the bottom surface using this flip-over technique by PFM, scanning probes. But we also developed another technique that I will show you, this Cherenkov stuff later, where we can really measure the inclination angle very accurately. And you see again, the PFM measurement is only on the top and the bottom surface, and the rest is interpolation. You don't know really what is really going on inside the crystal, 500 microns, as I said. So from the last slide, let me go back once. The point was, or our assumption was, if you go to, let's say, more dopant or so, or even up here in this curve of current, obviously the kind of inclination angle alpha must be increased. That was basically the outcome of this kind of measurement we did at the time there. And so that's why we said, okay, why not to flip over my domain wall completely? And the most extreme that you can do is actually you go for 180 degree or 90 degree, right, like shown. So that means simply that you take two crystals, you put them together, so to say, so that you have exactly two arrows, head to head, or you can do the opposite, tail to tail. So that was actually the assumption that that crystal could possibly give the highest conductivity. We measured that. You see exactly, this is the domain wall. This is exactly that wall here. This was worked together with Elisabeth Sörgel in Bonn. And you apply plus 10, minus 10. Well, there's enough current, but it's still on the order of picoamps. It's not nothing more than really on that order. So we didn't really win too much. So, okay, I have to say that that crystal was non-doped. So from that point of view, the magnesium was off. And hence, this domain wall that was really formed in here was really wiggling around. It was not really pinned. Well, that was really sad. So we continued, and then actually one of my students, Christian, he said, I have a glorious idea. Why not to take actually that crystal and pole it in a certain medium such way that I can control the inclination. So exactly what I said in the beginning, we don't go for the equilibrium domain wall, which we did on that, until that time, but we stop exactly in between. Well, the risky part by that is that you apply high voltages simply. If you guys know that actually cursive field of this kind of lithium niobate is so strong, so high, and we have 500 microns, so what we need for poling is about 10 kilovolts. Okay? So this is nothing that you have really normally in your laboratory, such kind of an amplifier. So that's why he said, I'm going into a helium chamber in order to avoid sparking, and hence basically have a very, very nice poling procedure. I can then stop, either I take either chromium electrodes or any other electrodes, and hence I can really engineer that. And bang, there was really a good result, because he could show that if you go for small voltage, plus minus 10 voltage ramping, the current goes up, as you can see nicely, up to a couple of microamps, as you see. So that was exactly a breakthrough. We had currents which are on the order of microamps already by this kind of technique. What is weird, as you see from this kind of IV curve, is it's ohmic on the positive branch, and it's rather diode-like on the negative branch. The explanation here is quite clear, because, as you see nicely, we have different electrodes being used on the two sides. On the top side, we have a chromium gold electrode. On the bottom side, since you can flip over for contacting, it's a pure platinum. So we're producing Schottky barriers, where the injection actually from the electrode into your domain wall is different on both sides. And hence, that is really reflected by this kind of asymmetry. What is clear to mention at this point is that we've done the engineering in such a way that you see nicely the inclination alpha that we have here points towards a so-called head-to-head orientation. So there are really the arrows, and if you digest that on your tongue, it simply means we're expecting electrons to hop along that domain wall to the other electrode, not the holes, because for holes we would have to engineer a so-called tail-to-tail, T to T. This is H to H, which is a head-to-head. So, yes, there must be hence any kind of inclination, and at the time there were really nice results from the Jülich group. And hence, this is actually a picture I took really from PCT, high resolution TM images. We had really from Moika already very nice pictures already 2 days ago. And hence, what we are very expecting is that obviously, if we go and would have a look on an atomistic scale, what we should expect for our domain wall is that this domain wall, which is inclined, this would be a macroscopic angle, let's say 0.1 degree, that it should be on an atomistic scale be made up of areas which are reddish, that means fully just normal ordinary 180 degree domain walls, which are non-charged, and then we have charged domain walls, plateaus like shown here in yellow, where we're going and just make one step or two steps depending on how large our inclination is. So what you see nicely actually in this model is that we expect electrons to hop from these charged traps, these are really now spatial traps, from trap to trap along the domain wall, simply because they can now really freely flow into this and hence be transported along that wall. So this was an assumption of a model, and we were not sure whether this will work. However, what you see is nicely clear that this is really confined to a very small area. These walls in ferroelectrics are really confined to a few unit cells only. You will see in lithium niobate it's about 7 unit cells only. Okay, so at that point we had to develop a new technique in order to see inside, because we didn't want to go for TM, cut open by focused ion beam our crystals, and that's what we decided to do, to go for Cherenkov second harmonic generation, thanks to the guys who already introduced into optics here. And what we take naturally is we take a femtosecond laser and we produce, so to say, this second overtone. So this is shown here, a 50 femtosecond laser, titanium sapphire at 790 nanometers, 5 nanojoule is full enough with a higher rep rate. We go into an objective, as you see nicely. This is a high numerical, so that means we can cover basically the full hemisphere, the upper hemisphere, so to say, and hence address any point there with this objective. We then place our ferroelectric sample in here, and as you can see nicely, we can really position the focus of that objective within this crystal in 3D. So you scan, so to say, X, Y, and Z through the full crystal, and then obviously what must happen is that the 2 photons, omega 1, are piled up as a second harmonic process in order to really come to cover the gap from 0 to 1. That's exactly our excitation level. And then we have 2 processes as a decay level. One is photoluminescence, that's exactly shown here. So this is a bright background, so you get shininess. So that's like in the visible range. Okay, it's different wavelengths here. But that's exactly what you see here, this photoluminescence, 2 photon photoluminescence, that's exactly the word for. And you get a direct transition, which is the second harmonic transition to the ground state. So you can filter off that part, you're not then interested in that part, but simply look on that part only, which is the second harmonic part, by using this kind of filter F1, go to the spectrometer, or you count them, so you do what you want. So correlating again, the position with any kind of measurement mimics that you have there, gives us then possibility to really look on this picture. And this is exactly shown here. This is now just an XY cross-section of a lithium niobate. Now I have to spend a word on why this is really working in this material. If you were aware during this kind of lectures also, you remember, at least Stefan said that once, he said, well, we need some kind of phase matching. Huh? If you have 2 photons coming in, the red ones here, we need some kind of phase matching until, so to say, we can really measure a second harmonic. Well, we could go up here and go down the same way. That would be elastic, right? But in that case, what we want to do is now we want to see something that is solidly stemming from the domain wall. So everything that is greenish here is only domain walls, and you see nicely the symmetry of these domain walls. You don't see something from the lithium niobate, because ordinarily, if you do this, you see the lithium niobate and not the domain wall. So the trick here is the following. If you have these photons coming in, and we need the phase matching, we can do this along 2 different directions. We can do this perpendicular to the incoming K vectors. That would be the G transverse, as you see here in this cartoon. Or we can do this also into a longitudinal direction, collinear. That would mean that the arrow would be different. That means the wavelengths would be different, right? So from that point of view, you have 2 different ways how to match to a certain G vector of your domain wall. And that's now the point. By this kind of hemispherical incident light, we find at any point when hitting the domain wall a phase matching condition per se for free. We don't have to do too much. We don't have to rotate, simply because the domain wall is so forgiving, giving us the phase matching for free. And that's really the nice thing. And then the second harmonic, Cherenkov light, comes out at a larger angle. So it's not the same angle like your direct light comes out, the second harmonic, but the Cherenkov angle is much larger. You see that here. So what you do physically in your experiment is you position your detector at these positions, left and right, or you just, like in a dark field experiment, lead or so, you just block the center beam. Okay, you just take the apex beams, and if you do so, put them on the back focal plane, you see exactly the symmetry of your system. So you can also check locally, what is my symmetry of my system somewhere inside. So this is really nice. So let's go back to this nice picture. We see now as a cut into the sample all the domains that we have been producing. And if we do that now along the direction, this is now the C direction, as you can see, we can really cut through all these things. This is a single domain into the depths, and these are the domain walls that are really cut now. By some interpolation, we can really refine the resolution, and hence basically see that now. In a 3D animation, you see actually this is changing, which means we're going zack, 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 like in a salami, we're going through the crystal and basically stitching together all these into a 3D frame. And what comes out is exactly this, that we have now the domain wall isolated from the rest. It looks a bit blurred in the width, and this is simply due to the convolution. Your beam, so to say, has to be convoluted with the domain wall that is really still a delta function, or something like a delta function. But that's actually something you can correct for. But nevertheless, the resolution of how accurate you can really resolve these angles is really low. It's 0.08 in this case. And what we've been doing now is the following. We've been doing actually a comparison between all the PFM results that we have here and this Cherenkov. So the PFM, remember, we measure on the top and the bottom surface. And here we go really through the crystal and really measure the inclination. And you see nicely, for all these different materials, that all these inclinations really coincide very well. So the big relief is now that we can look inside the system and really see locally how this kind of inclination goes. Now, this picture of a straight wall that I was really putting up in the beginning, I mean, this is, I would say, Asian. This is really not true. Because if you take any kind of material, and I have 2D materials here, tons of, and you see basically this would be really a piece of paper, and if I would really make a domain wall that is realistic, you're going to wrap it this way. So if you look on this paper now, you would say, well, that's exactly, it has some certain roughness. Huh? And if you take graphene or any kind of other 2D materials, that's exactly the same thing. They're all rough. And if you go really and look on it on a landscape, you see, oh, their heights and lows, and hence the electrons that want to flow along this 2D material, they need to find their path, which is the easiest to go. Huh? If you go on a hiking tour, even here on Corsica, you don't go actually always down to the valleys and up the next hill and so on, because that's too sturdy. So you want to stay on the top, actually really walking around and basically not really walk through to the pitfalls. So that's the same for the electrons here. So this is very important, to have a local picture of where these electrons want to travel. Now, Benjamin in my group said, I want to know it now. I want to combine this nice technique together by applying this kind of poling procedure that you saw before from Christian. That means he's applying bias voltages in order to really incline the walls up to 350 volts. But he wanted to, at the same time, to measure the current that is flowing along the domain wall. So we're combining the two things, current measurement on the one side and inclination changing. And you see actually as a function of time, this is real time here, you go and just increase linearly the applied electric field. By the way, 350 volts divided by the thickness of 200 microns here is still a maximum field which is ways below the corrosive field. So we're not switching, but only we're wiggling on the wall. So we take a force, electric force, we pull on that domain wall, and that's exactly at one certain cross-section of what you can see by applying this kind of field. You see actually how the domain was then really, this one goes in, as you see, and rather than actually stopping. So this was a XY picture. On the other side, you see that the reddish curve, this is the current now, it goes up, and after having pulled the system and then going back to really 10 volts, bang, the current is up here, 10 to minus 4, 10 to minus 3 amps. So huge currents that are really flowing along one single domain wall. So that's the domain wall that you see here. Now, pointing this into a 3D system, as you see again here, this hexagonal wall, that's why we're rotating it, it's fully hexagonal, ends up in something where the inclination, this is exaggerated though, but where the inclination is really tailored. So, please have a look that we have been coloring. Reddish means always head to head, And bluish, there's some areas down here, there's some area coming up here again, means tail to tail. So what does it mean again? Remember, head to head means the arrows of your order parameter are really pointing towards each other, while tail to tail means just the opposite. Or in other words, all the reddish areas are good areas for electrons to travel, while the blue areas are good areas for holes to travel. So we see that here directly. So the model, combining now exactly this inclination together with what we just saw, is actually that we have obviously traps along that domain wall where electrons can really sit, and hence there are some neutral domain walls, non-charged, neutral ones, and there are the charged ones, and we get, like in a staggered stepping, so to say, a hopping mechanism along that wall. So this is actually a fantastic idea of modeling, of how to model this here. Well, beyond exactly these kind of PFM measurements, we have now these kind of Cherenkov, and we can really look inside where are these traps now. Now, in order to really get this more quantitative, we need some theory there, and we have been looking on a so-called random resistor network, and the second one is actually a charge hopping model. So these are two publications actually into this direction. And let's go now exactly and explain a little bit more what's really true. So the model, or that's the assumption at the moment, is electrons can hop along a domain wall simply because they are charged, so to say, fractions of a domain wall. At that time, this was basically our picture, and lucky enough, in 2016, there was Julia Gunnison, together with Eckhard Sallier in UK, that did some very high resolution TEM measurements. So we're coming back exactly to that technique. They cut it open and do just one single measurement on one of these domain walls. So they cut out one of these sections, but this is a fully neutral domain wall. I have to say, the reddish ones in my picture before. And they said, okay, let's measure simply how wide at room temperature is this domain wall. So this is exactly one of their results. This is a TM picture, and all the black dots that you see here are the niobium ions. So we have a crystal lithium niobate. You pick out only the niobium ones. You remember from Moika's talk, actually, you can really be selective on one element only. Here it's the niobium. And hence, what you do is actually you just map that across such a domain wall. Polarization left is up, polarization right is down. So we have a wall, and as I said before, tangent hyperbolicus in the beginning, historically, that's exactly what we expect to have here. So that means from here to here, there should be a uniform change. Now look basically at this domain wall, how this really looks like. This is realistic. It does not really change uniformly that across the wall that goes here from the purple line 1 to the 2 here. We have a changing across this direction that is uniform, but we get some steps inside the wall, steps to the right, steps to the left, and so on. So it's really wiggling forward, wiggling backward, wiggling forward, wiggling backward. And that's exactly what we had before here. This is exactly the best model. You see the wrapping, it has some certain roughness. And this roughness is on the atomic scale. It's an atomic scale roughness by hopping forward, head to head, by hopping backward. So in a neutral wall, always in nature, what you have is that your wall is not a single unit width. It has some certain width. In that case, it's 7 units. And you always get from top to bottom, you go forward, backward. So that's actually the picture of a neutral domain wall at room temperature. And even if you cool it down, it doesn't get better. You cannot avoid that. That's nature, because it's a random step to the right, a random step to the left. So the picture that we put up actually is not too wrong. That means simply, yes, a wall or conductivity in a wall has to do with these kind of steps. The only thing that is different if you go to such an inclined wall is that we take this wall now and we bend it. So we're playing with the fraction of head-to-head to tail-to-tail fragments, right? So inclining the wall means simply that we have now more, let's say, head-to-head fractions or more tail-to-tail, depending on whether we go alpha negative or we go alpha positive. So that's a very good point, that we were really lucky that Julia was doing this work. And in fact, this means now that we can explain this kind of domain wall conductivity that we have here, actually through the measurements from Christian and these very high currents that we were really measuring. So Benjamin, in my work, he was taking these kind of really pictures. These are the pictures that we just obtained by Cherenkov before. He takes it, and then he unwraps that. So if you take the circumference of such a domain wall, so let's say this is now my domain wall. You see, okay, it's a quadratic, doesn't really matter what it is at the moment. And what you do simply is actually now you make it open like a world map, and then you can really look on this with the boundary condition that the left side has to match the right side. So that was really a trick he was doing and saying, okay, I'm unwrapping the wall at any stage because we have the real-time pictures. I can unwrap this. That's exactly from 0 to 360 degrees. That's one full circle you go around. And now you see again these kind of reddish areas, which are the head-to-head, and you see the bluish areas, which are the tail-to-tail. Remember what that means? Simply electrons or hole hopping. So that means his idea was to say, well, if I have reddish areas, that means the probability to inject electrons here on the top. Remember, this is 200 microns. It's not a unit cell. It's 200 microns. I'm injecting electrons here. I can calculate the probability of where this electron wants to go. Does it want to go here? Does it want to go here? Does it want to go here? So I can follow up in a model the trajectory of such an electron on its journey through the domain wall. And that's exactly what he did, and said, okay, I'm going to take this full picture that we have now, this world map, this unwrapped inclination map, together with a so-called random resistor model. You see, basically what we do here is actually we take a squared lattice. You can take any kind of lattice, doesn't really matter, triangle or pentagon or whatever. In the end, actually comes up that you're going to basically put a superposition of a grid over your measurement data in order to interpolate on the different resistors, here reddish or bluish. So now it's up to you how discrete you want to have this. You can have a very dense lattice. I mean, it doesn't really make sense to make it more denser than actually our data is. So our data basically is 1064 by 1064. So from that point of view, that's a very huge data. And he does then the following, saying, I can now apply either a point electrode, this is my AFM, when I'm doing CAFM on the top, or I can even put up a platinum electrode if I'm doing really, let's say, macroscopic measurement. So I want to show you and share with you as the result that you have basically when you apply a local electrode, when you do really CAFM measurements, it's clear that the injected electric field now drops within a certain area, and that's exactly what we see. That means mostly, if you put it down up here, is that actually at this position, so to say, the field will penetrate, and yes, we will have a larger current that goes in here and then actually trajectory through. So he has done tons of data and really calculating at which positions are the good positions, which positions are bad positions to the inject currents. And the outcome is twofold. First of all, we're able to really correlate this conductivity that we get from the AFM, from the CAFM, with exactly the inclinations that we have from the Cherenkov. That's the first thing that is really good. That means actually really high currents at these apex. If you go back, you see the apex are really here, 1, 2, 3. And if I go back once more, that's exactly in the corners where we have higher conductivities. Second experiment, we can correlate actually this conductivity also to the measurement, so to say, both that comes out theoretically from his random resistor modeling. So that means actually we can correlate, okay, the good values here, a little bit of deviations here, on exactly where the current wants to flow. And so the outcome is right, that we have now a trajectory of where the electron really flows. It goes in on the top here, goes out down here by this random resistor model. Well, we want to know it much better. And we said, okay, I mean, resistors is nice, but we want to have now a more accurate view by a charge hopping model. Let's go for charge hopping and really let's take actually now a system where we have, again, this p-plane. That means, so to say, we have two domain walls, left and right, like is shown here in the cartoon, where the two walls are really inclined in parallel by 0.347 degrees. So this is the same thing like in the beginning, periodically pulsed lithium niobate. And what you see nicely here is actually, if you do so, you always get, so to say, a domain wall, and you see this very nice from the PFM phase here. You see a domain wall on the right side, and you see a domain wall on the left side. So let's pick out this kind of out-of-plane polarization. Okay, This is a domain. And now, if it's a domain, certainly it has a right side and the left side. And they go both in this way, 0.37 degrees. Now, if you digest that on your tongue, it simply means that one of these walls must be a head-to-head, while the other one must be a tail-to-tail, right? So that means simply that we have now two different types of walls within one and the same crystal. And you can address that by taking your scanning force microscope again and you scan over it. So you do, instead of doing PFM, you then CAFM, right? So what does that give? Well, you see nicely actually, this is actually the cartoon towards the dashed ones and the dotted ones, means it's the right or the left wall. The dashed ones are the left ones, the dotted ones are the right ones. Now, if you compare that to the CAFM picture, you see always high currents for the right ones. And in fact, these are the head-to-head ones. Taking the cross-sections is really reinforcing our assumption that the right ones are giving a much higher current than the left ones, because there's no current there. So, Xiuyu said, well, let's do our quantum mechanical modeling by a hopping mechanism. Let's take a hopping, we take one of the elements, we do again a discretization. We take just one unit cell, we discretize it, there's a head-to-head, there's a tail-to-tail here on that side of the wall, and hence there are electrons or holes that can flow here. And let's now make a 3D modeling of this hopping, so that we're calculating the tunneling probability of that guy to tunnel in any of its neighboring or next neighboring actual positions. So cut the whole system 3D open in such a way. In order to really do this calculation, we needed transport measurements of activation energies, because the hopping mechanism can be activated. We can apply a voltage, but it can also be thermally activated. And that's exactly what we did. We took a sample, cool it down to really cryostatic temperatures, and hence really measuring the activation energies that you see as a function of time. And you see nicely, obviously, there are three different regimes. One actually typically popping in above room temperature, one typically between 100 and 300 K, and one below. And typically the values of our activation energies are really in this regime, 0.2 to 0.3 electron volts. So we take this value, put this into the modeling of the hopping mechanism, and what comes out is exactly this one here, that we find, there can be really right-handed, or the right domain wall really enhanced currents in the model. This is a model only. And hence these are really the electrons, hence it must be an n-type conductor. We can also do the modeling for the holes, and hence actually oppositely to that one, you see nice, it's the left side. So if you go for hole transport. So we see that the model is really good, tunable. We can really put the activation energy and compare now the experiments with the theoretical value. And you see nicely that, yes, on the right side is really coinciding with what we find in the CAFM picture, really on the right side. And hence, yes, it's an n-type conductor. So this is really good news. You have the choice now with the system, if you want to really engineer an N or a P-type, or you can even make a PN junction, whatever you want, simply by combining these two things. So that's really nice. One thing more, what she found also, Xiuyu, is, again, coming back to my experiment here. Remember, that's the roughness. The domain wall is not straight. So this is a straight wall where the hopping is really regular. Now imagine that you have more kinks, irregular or a roughened wall like this one is. So what the electron then sees is a landscape that is not really regular. It's not always uniform, but actually it has to hop to different spots along its journey. And that's exactly the point. This roughness now, if you do that compared to the case A, is increasing the conductivity by a factor 10 to the power 6. So what is the message there? Take home. If you want to have good conductivity in the domain, well, make it rough. You have to find a way to roughen it. For instance, apply an AC voltage or something in order to, you have to disturb it a little bit. Rough walls are much better than actually straight walls, even if they're inclined. Okay, so this is exactly the point you see here, what comes out, the smooth walls, the rough walls. And that's exactly then reconfirming actually Julia's work here. Now let's go for the electron gas. We want to now, simply because we have now, in fact, enough conductivity, measure what is really going on, and it's quite clear. We want to really do something like this kind of really quantized actually stepping. Okay, we're not there yet, but I can share with you exactly what we have done so far, and that's exactly shown here. So we need, in order to have really conductivity, enough states in which we can really tunnel to. That means simply we have to have a band bending, and that's exactly what we have proven so far, below the Fermi level, which are filled with electrons. And for this case of really Hall measurements, we take only the n-type walls. So we're engineering only n-type walls in our crystal, and you know now how this goes. We need exactly, so to say, a head-to-head configuration. And once we have this, actually, we can apply, so to say, to the wall enough electrodes. And that's exactly what Hendrik is doing at the moment in the group. He's taking exactly kind of domain walls, and hence applying at least 4 electrodes. So we're doing an experiment where we have 2 top electrodes, 2 bottom electrodes, and hence we put this into a magnetic field that is really tunable, up to 1 Tesla, in fact. And so what we do is now we measure exactly in the conventional standard way the Hall transport. So having these 4 electrodes, you can combine the different 4 electrodes into different versions. You can really make asymmetric or symmetric measurements, and you can also have longitudinal transport with respect to transfer. So one of the experiments that comes out actually is that he's measuring really this the sheet resistance R that is shown here as a function of the magnetic field applied, and you see nicely that for this domain wall actually it's really going up linearly. So we have a quantitative value, how many electrons are really traveling as a function of field. We put this into a model, and what comes out is typically 10 to the power 12 electrons on a centimeter squared. He did a reference experiment by saying, okay, why not to rotate now? This is actually the rotation angle, phi. Why not to rotate the magnetic field with respect to my sample? So you have your wall, and you rotate this off. It's quite clear what happens. Basically, you get a collinear alignment with your magnetic field with respect to the transport direction, and all conductivity, all resistivity, the whole resistivity should vanish. And that's exactly what we see from the values at a certain point. This one here was a measurement. We go down, and in fact, we're going really to 0 at 0.5 of pi, so 90 degrees. So this is really a very good confirmation. We're working at the moment exactly into this direction, to this at different temperatures, and naturally, this was the 5% magnesium dope, because that's the one where the engineering works best. Also for the other ones, actually, that are really good. Now, let me come to an application part. Where can we use these domain walls now? And I would like to, first of all, break the ice for a technique that has popped up 15 years ago, called ferroelectric lithography, which has to do exactly with the domain walls, and then really show you the application in a real domain wall memory, room temperature. Let me step back once and really compare the thin films PCT, BTO, or even BFO that we had before, again with these single crystalline systems, lithium niobate or tantalate or whatsoever. What is the difference? One of the big differences is that in all these materials, you know, if you do a polling, and you remember also from my first talk, we get screening charges. We get, let's say, charges inside, we get built-in fields, and so on. So from that point of view, all these kind of materials like PCT, BTO, are known that the compensation might come from internal. So that means the following, that charges are migrating from the center, from your bulk to the surface in order to compensate and shield the effective field. Lithium niobate, lithium tantalate are known that this shielding can only exist from external. So that means simply that no charge inside the system will ever flow to the surface. That's good news simply because then you can take precautions if you go to a very good environment, let's say vacuum or so, then you're sure that nothing will happen inside the crystal. The crystal will stay the same all the time. The consequence out of that one is that the shielding fields, you see that here, at the domain wall are really at the position of the domain wall itself. Or in other words, we get a stray field that is strong, very strong for these materials if you have a domain wall like this, at this position, in contrast to the other ones where the shielding also can happen inside the domain. So now imagine we would have here charges on the surface, and we would take any kind of materials that we would like to deposit onto the surface. And you see nicely what happens in this case, where the shielding is internal, the material would rather like to go towards the domain. meaning, okay, this is negatively charged, my material to deposit is positively charged, so the attractiveness is rather in the domain. In the second case, B, this attractiveness is to the wall only. The stray field is strongest at the wall and not within the domain. And that's exactly something we have been playing with a lot, saying, okay, why not you take materials, and this is just a rhodamine 6G, which is just a color. So you're using this basically to staining. Okay, in early times you have also been using this for doing lasers. You mix it up actually into a liquid and basically make a so-called color laser at this wavelength. You see nicely it's 560 nanometers, between 30 nanometers tunable. So we deposit this exactly along the domain wall rim, and hence we can have only a trapping of these materials, of these molecules at that wall. Second example we did together with some biologists is actually we have been using just a DNA molecule. And you know these are spirals, so it's a double helix. And having simply a sorting of these molecules along these domain walls. And these molecules have been stained also with a color stainer, which is JoJo1. So it's a green fluorescent molecule. And that picture, what you see here, is simply a fluorescence picture. So these domain walls are very nice also for other purposes, not only conductivity. Here comes an example from Alexander. He said, okay, why not to deposit something like metals, like platinum wires? So you can stain your domain walls. If you don't see them by eye, you can basically stain them and really nicely increase the color. And moreover, he said, okay, why not to make another wire that is addressed along that domain wall and hence apply currents, so to make really a switching. Fantastic, does work. So these domain walls have more purpose. Now, the recent application we did actually is a memory. Really a thin film lithium niobate memory. So in that case, you have not been using the thick 500 micron, but actually a thin down material. So in that case, the material is only 200 nanometers, but still single crystalline. There's some techniques how to do that. If you are interested in that, ask me later. But nevertheless, they are so-called thin film lithium niobate. The idea is actually to deposit this here, and then actually to split off a thin film of certain thickness. In order to do so, we have here a very nice TM picture from this one, from this sample. You see actually the thickness typically is on the order of about 100 to 200 nanometers. So, Thomas in my group, he did the following. He said, okay, why not to write, as we always do, domains in this kind of thin film. So we're doing PFM measurements, writing domains, squares, and then measuring IV curves at different positions, 1, 2, 3, 4. So, again, up and down domains, as we know, from the macroscopic view, and then measuring the currents, and you see nice, there's some currents going up and going down. So that means at position 1, the current, actually, what is the reddish? Nothing. No current. That means exactly, but that's my reference. If you go to position 2 or 3, you see nicely position 2 or 3, these are the currents actually that we are measuring there, and position 4 here has the highest currents. So why not to make now a memory device out of this? And so what we took is actually such an area, we said, okay, if you know position 4 is the best, let's do an electrode just on top of position 4, top electrode, bottom electrode, and do a measurement. And we did this exactly, and we sweep the voltage, as you see, between 0 and 20. That's the reconfigurable voltage. And we measure really between 0 and 5 volts for reading. That's exactly the point. So, you remember, only 2 contacts, top contact, bottom contact, and in between there's a domain wall. So, large voltage, 20 volts, actually can switch that domain wall from a low conductivity into a high conductivity. You see that here. And if you go back, we can also reverse that action and switch it there for a low conductivity if you go to minus 20 volts again. So this is actually the loop for switching by applying high voltages. If you go up to 5 volts only, you can measure the state, this one, high conductivity or low conductivity state. We did this now many times. You see 10 to the power 5 times, which is important to do for a memory in order to really show that. And what is intriguingly nice is that the distance between these values of currents, as you see here, 10 to minus 10 or 2 times 10 to minus 10, 10 to minus 6 is really low. We call this the memory window. That's the word, the buzzword for any kind of such application. And if you compare that, for instance, to other memories, typically they have 10 to the power 2, 10 to the power 3. This is intriguingly nice because it's a high value, and you see nicely if you do distributions, we're very far away. There's more to say, like for instance, we can really measure now also AC conductivities in these walls, or we can also measure the dielectric constant of such a wall by using a technique called OCT. This is something that you're possibly aware of when you go to your doctors. But in due time, actually, what I would like to do is really get you to the nice videos in the end. Because as I said, this is really cool. Huh? So, what I want to show you is actually that this kind of Cherenkov method has a very nice and intriguing way of really looking into your crystal, looking on domain walls in a way without destroying it. And we've been doing this, we are trying to do this with this Cherenkov for really poling and switching domain walls and domains, and also looking on phase transitions, because the theoreticians believe you only on these kind of things always if they love phase transitions. Me too, by the way. The tricky problem is that lithium niobate, as you guys know, and I said, has a very high Curie temperature, typically of 1,300 centigrades. So we don't have an oven or a system yet that is really working up to there. So we had to do these experiments as a proof of principle experiments with a different crystal at lower temperatures. And Lucas in my group, he was then taking actually a system which is triglycine sulfate, which is also uniaxial. It's monoclinic and has a phase transition temperature at 49 centigrades. So it's really every appreciable, very nice, but we can really intriguingly see the same physics. So this is a unit cell. The polarization is aligned along the B-axis, and what we see here already with this Cherenkov is we're looking on the AC plane. That is exactly, it's anisotropic, by the way, and the polarization is pointing out of plane towards you. And we see nice domains. You see the inner region, the outer region. That means we have up, down. What I want to show to you now is the following. In the first experiment, that we apply a voltage. So we do again the slab. You can take your point, your tip, or you can take two electrodes and apply a small voltage. This is 4 volts only. You will see it's full enough for this crystal to pole or to change. And so now this is exactly the dynamic. This is real time, by the way. You see the voltage up there, 1 volt, 3 volts. And you see nicely how these domains they meander, they join here. So, and basically they crop back simply because applying a voltage means we are applying an electric field that is disturbing the equilibrium. So we don't have up and down equilibrium anymore, but we're going in favor of one polarization. In this case, it was up polarization. And all these reminders that are here are still there, that we can see them because they're scattering by the second harmonic picture, by the second harmonic, so to say, and they stay in the crystal. We believe this is a signature of really the reminders of Bloch lines that we see here. Second experiment, the same material, but now we do a different system. We go and crank up the temperature over the Curie temperature that is here at 0. So this is relative, T minus Tc. So we start about 5 degrees below the Curie temperature, and we go over the Curie temperature in order to see the vanishing and recrystallization of these domains. So again, you see now this in full 3D. By the way, this Cherenkov is really fast. We need per picture 1 millisecond. So that means simply that you can really track this in full 3D. Now you see the temperature goes up, goes up. Now phase transition, back. Okay, it's all gone. Now we go down again. Just wait. Okay, there it is again. So you can see actually how it recrystallizes and which domain is then finally really meandering together with each other. So I think this is really an interesting thing to really adapt for any kind of systems. And we are on the moment, not only, as I said in the beginning, looking on these kind of ferroelectric walls, but you can adapt this also to so-called ferroelastic walls, but you can also see this on magnetic walls if you want to. So it's simply a question of how you do it and what kind of signal you have. So let me summarize. What I wanted to show to you really in this talk is now that we have really large domain wall conductivities in these kind of domain walls, simply because we have a little bit of a good feeling how to engineer that in these walls. We can tune the inclination, we can tune the roughness, as I said. This is very important in order to go to, we have a 2-deck, which is really having a really now a whole signature for transport. You can engineer both N or P-type walls if you want, simply by using this kind of head-to-head or tail-to-tail domain walls. And you can go for novel memory devices, large memory windows, high endurance, low fatigue. And last but not least, I would like to again emphasize on this kind of Cherenkov stuff, second harmonic, because I think this is giving us much more happiness than really cutting any systems by TM. Thank you very much for your attention.